And the last thing that I'm going to talk about with respect to dilutions and concentrations is how we can determine concentrations using an analytical instrument. So the spectrophotometer, or often just the spectrometer, is something we call an analytical instrument. We have an entire year-long chemistry course, Chem 341 and Chem 441, dedicated to analytical chemistry. So upper division chemistry majors take this class. And for those of you that are chemistry majors, this is something that chemists do as a profession. They use these types of high-tech devices to determine concentrations of unknown material. For example, when you pick up like a box of cereal or a packet of, I don't even know, a candy bar or whatever, right? And you look at the nutritional information, do you know what I mean? That tells you how much sodium is in it, how much sugar is in it, etc. Okay? Some chemists had to use analytical instrumentation to figure out what those concentrations are. And here is how the spectrometer works. Okay, so you have what's called a cuvette. And a cuvette is just a fancy test tube. Okay, it's just a test tube that's often square, or I should say it's rectangular. So it's got this very regular geometry. So it has a specified width. That is typically 1 centimeter. It can be different, but almost all spectrometers have, it's a 1 centimeter thick cuvette, or 1 centimeter thick test tube. And you have some solution in there, okay? Now this solution has to be something that will absorb light. And we'll spend a lot of time talking about that later on in the semester. What molecules absorb light, what molecules don't absorb light. For now, we'll just say we have a colored solution, okay? And because it's colored, that means it's absorbing light, okay? And hopefully we'll be able to dive into this a little bit more in your virtual labs. And so what this instrument will do, it'll pass light through at intensity IN, and it's really bright. So the size of this arrow indicates that there's a lot of intensity of light passing through. And we should also note that this could be visible light, it could be ultraviolet light, it could even be infrared light, or it could even be X-ray, depending on what technique we're using. So in chemistry, more often than not, these are the common. UV-Vis is very common, but IR and X-ray, they are also common as well. Most of what you will be exposed to as a beginning level chemist is ultraviolet and visible light. But like I said, we can use infrared or we can use X-ray. We'll talk a lot more about those different flavors of light as we progress through the semester. And so what's going to happen now, the solution, depending on its concentration, will absorb some amount of this light. And so the instrument measures the intensity of light coming out. And of course, this is in reference to the intensity of light going in. So the very first thing you do is give it a blank measurement so you know how much intensity in there is. Then you put your solution and you see what the intensity out is, okay? And look, this ratio T, that's called the transmittance. And this transmittance is always less than 1, right? I out divided by I in, because I out is always less than I in. So the sample has absorbed some of that light, okay? Transmittance can be converted into absorbance by taking the negative logarithm of the transmittance. Okay? So absorbance and transmittance are kind of like equal and opposite, all right? So they both reflect the same thing, just one looks at how much light has been absorbed, in the case of the absorbance. The other measurement looks at how much light passes through, in the case of transmittance. Either works, But often in chemistry, we use absorbance, and this is the very famous Beer's law equation. Oops, I'm going to erase that so I have room to write. Okay, so Beer's law is given by this equation here. So let's break it down. Okay, so this B, that's our path length, right? So often that's about 1 centimeter. This, recognize that? Brackets, concentration in molarity. Okay? In molarity. And this term's, this little e right here, that's what we call the molar absorptivity. And that has units of 1/centimeter per molarity. It's a crazy unit, but the idea of the unit of this is when you take the units of this, 1/centimeter per molarity, times the path length, centimeter, times the concentration, molarity, all of the units cancel because absorbance is unitless. It's an arbitrary, like, how much light did the sample absorb, okay? And so the way this Beer's law works, here is a graph of Beer's law. So here's the absorbance, A, versus the concentration, C. And what a chemist or a scientist would do would make several dilutions. So they might start, for example, with their stock solution way up here, right? Because if you follow this on the scale, the stock solution would have a very large concentration, and you would make serial dilutions. So in other words, you would dilute this thing over and over and over and over again, okay? And so each one of these data points represents a new solution that you would have made from the stock solution by continuing to dilute it over and over and over again, okay? And what you get is this beautiful straight line, the slope of which is equal to the molar absorptivity, okay? And so now then, if you have an unknown concentration, which I'll draw with a box, so now suppose we have an unknown sample, like maybe somebody gives us a, I don't know, a commercial product, and we want to know how much of this stuff is in it before I sell it to the public, all right? So I would make a stock solution of that thing. I would make these serial dilutions, and then my unknown sample, I would compare. So my unknown sample, I would be able to measure the absorbance. I wouldn't know the concentration of my unknown sample, right? It wouldn't be told to me. However, I can put in the spectrometer. The spectrometer is going to tell me what the absorbance is. And then now I can follow on my graph and say, aha, now I know what the concentration of that unknown had to be, okay? So it's a pretty cool technique. I do this technique in my own research. I use IR. I use infrared light in my research to do spectrometry. And we have all kinds of flavors of spectrometers in the chemistry department. We unfortunately do not have an X-ray spectrometer. However, we do have several UV vis, infrared. We even have a type of spectrometer called NMR, which is nuclear magnetic resonance. And that's very cool. That is a giant, giant instrument. It's about as big as a VW, or it's about as big as a small car, I will say. But it's cool. We have an instrument like that students get access to using here on campus. Okay. So the last thing I'll say now, just an activity, so if we can follow through. So let's suppose we have a green stock solution and we make several serial dilutions. So which one has the largest concentration? So hopefully you can see that C, it's like the darkest green color, right? So this would be the most dilute because, you know, maybe we've completely diluted it so you don't even see the green color anymore. That can happen. This would be the second most dilute, the third most dilute, and then this might be the most concentrated. Okay, so that's all I'm going to say for now about this video, folks. I will see you on the next one. Hasta luego.